This is camphor. Right? I'm going to add about 0.5 grams of camphor into this long neck round bottom flask. Right? Okay, so this is 0.526 grams. It's not exactly 0.5, but little more than 0.5. That's okay. I'm going to keep this. 0.527 grams of camphor. Okay, that goes into the round bottom flask. And then add 2.5 ml of methanol solvent. Okay. One ml, 2 ml, 2.5. Right. And then add a stir bar, and we need to dissolve the camphor into methanol. So I'm going to stir this on a hot plate to dissolve the camphor into methanol. Clamp the flask on a stirrer and start spinning. This will dissolve the solid camphor into methanol. This doesn't take a long time. I'm going to prepare the sodium borohydride to put that into this flask. Sodium borohydride is our reducing agent, the hydride source. Right? We have camphor reactant and methanol solvent in here. We need the reagent. This is sodium borohydride. It is inside this tin. It reacts with water, right? It reacts with the moisture in the atmosphere. So we kept it inside this tin and in this plastic bag and in the form of pellet, right? It's pellet because the surface area is small compared to a powder. A powder will have a large surface area and it can react with the atmospheric moisture quickly. Now this is pellet, it reacts slowly. We need 0.5 grams of this sodium borohydride. I'm going to break this into smaller pieces. Alright, so here's it. Put that in a mortar and use a pestle. Break this. So broken into smaller pieces, right? So remember this sodium borohydride. We are going to use this in our lecture, in our reactions a lot. Sodium borohydride is a good hydride source, H- source, and that can reduce aldehydes and ketones into alcohols, right? Okay, so that is this. We need a 0.5 grams. Okay, 0.524 grams, 0.523 grams, right? Let's close this windows. 0.523 grams of sodium borohydride. That's how much I'm taking. I'm going to put the remaining back into this plastic bag. And keep it here to keep it away from the moisture. Okay, good. Okay, I'm going to add the sodium borohydride to this reaction mixture of camphor and methanol slowly, right? Because sodium borohydride has the hydride H minus and methanol has the proton H plus on the oxygen, right? The alcohol group of the methanol is a good source of proton. So this hydride reacts with the proton and gives out the H2 gas. H minus and H plus makes a bond and create H2 gas, which is a flammable gas. You can see bubbles coming off from the liquid. That is H2 gas. And this is one of the post-lab question. What gas is coming out of the flask? Right, H2 gas. And this reaction could be an exothermic reaction. If it heats up too much, I have a water bath to cool down the reaction, right? Okay, so we need to add slowly. I'm going to use a spatula to add slowly, and you can see bubbles coming off. Okay, I'm going to add more. Okay, here I'm adding more, and you can see the bubbles. Okay, so let's spin to let them react. Okay, for next 5 to 10 minutes, I'm going to add the sodium borohydride in smaller portions slowly, right? And when it heats up, I can touch this round bottom flask. It's not too hot. If it becomes too warm or too hot, I'm going to use the water bath to cool down the reaction. Right. Okay, it is a little bit hot, so look for the water bath to cool down the reaction. It turned out to be now you see a lot of gas coming out, but it's not too hot. I can touch this. After all of the sodium borohydride was added to the reaction mixture, I'm going to put an air condenser and do a reflux. You know what is reflux? We'll heat it to boiling temperature. The boiling temperature of methanol is the boiling point of methanol, right? So heat it to the boiling point of methanol, and when the methanol evaporates, it condenses at this cooler part of the apparatus, the condenser, right? The methanol condenses and goes back to the flask. So it's going up to the condenser and going down to the flask. So it's kind of a reflux, right? Okay, we need a aluminum block. The book says sand bath. You can use sand bath like a water bath. Remove water and put sand, that is sand bath, or you can use a heating block. The purpose of the sand bath or water bath or a heating block is to spread out the heat evenly from all directions of the round bottom flask, right? Without this curvature, the hot plate is a flat surface, and the heat cannot transfer from all direction. So I'm going to heat the block first. Aluminum is a good conductor. That is why we use aluminum foil in our cooking. Right. Okay. So once the aluminum block is hot, it can conduct the heat from all direction into the flask. Okay, the reaction mixer is boiling. I'm going to let it go for 2 to 3 minutes to complete the reaction. After 3 minutes of reflux, let's stop heating and let the reaction cool down to room temperature. Okay, let it cool down to room temperature, and then we'll put the reaction mixture into this flask that has some ice. Okay, after cooling to room temperature, pour the reaction mixture into this polymer flask with about 5 grams of ice. Right. Looks like it's stuck, like a semi-solid, a waxy substance. So we need to scrape out using a spatula. Okay, let's use a spatula to scrape out our reaction mixture. Or use some water, distilled water or DA water, to rinse the compound from the flask into the ice. Okay, your compound will not dissolve in water, right? It will stay as a solid, as a precipitate. We're using water just to rinse out the solid, and then we'll separate the solid using a vacuum filtration technique. Okay, so after rinsing out all of the compound into the flask, I'm going to do the vacuum filtration, right? Turn on vacuum. Okay, after a few minutes of drying under vacuum filtration, I'm going to remove this solid product, which is isoborneol and borneol. It's a mixture of borneol and isoborneol. Alright, let's transfer that into one of these Erlenmeyer flasks. But before that, let's remove the solid product. Okay, this is a crude product. It has isoborneol, borneol, there may be some unreacted camphor, and some water. Water comes from the washing, right? We used water to rinse out our solid during the vacuum filtration. So how do you remove water? We're going to use the dichloromethane. This is an organic solvent, non-polar solvent. So when you dissolve the solid in dichloromethane, it is a soluble, the product is soluble in dichloromethane, but water is not soluble in dichloromethane. You'll see, if there is any water, you'll see water drops floating on top of the dichloromethane solvent. And then we can use an anhydrous sodium sulfate drying agent to absorb the water drops, right? So let's do it. Into this Erlenmeyer flask. Okay. And add about 5 ml of dichloromethane. So it's an approximate amount, you don't have to measure. Okay. And dissolve your compound. Okay, you can see that this, okay, you can see that your product is dissolved in dichloromethane, and there are some droplets floating on top of the dichloromethane. That is your water, right? Water is less denser compared to dichloromethane, so it floats on top of the dichloromethane solvent. So we're going to use a drying agent to trap the water droplets before we go for the IR and NMR spectroscopy. Having a water drop in your sample will give a false peak, right? A false peak, a false positive, because isoborneol has an alcohol group, and we are looking for the alcohol group in the IR spectrum. If there is any water in your sample, water also has the OH peak, right? You know the formula of water, very similar to alcohol. So the water will give a false alcohol peak. To avoid that, we should remove any trace amount of water from this sample. So we're going to add a drying agent. It could be anhydrous sodium sulfate, anhydrous magnesium sulfate, anhydrous calcium chloride. So any of these could remove the water drops. Okay, so here's the anhydrous sodium sulfate. Right. So after adding the anhydrous sodium sulfate, you can see that the water drops are gone, right? We don't have any water drops. They're all trapped by the sodium sulfate. So I'm going to transfer this liquid, which is dichloromethane, with the product. Okay, pipette out the liquid and transfer it into another clean, dry Erlenmeyer flask. That is dichloromethane and your product, isoborneol and borneol. Right. The water drops are trapped in here by the sodium sulfate. Okay, now let's rinse this sodium sulfate with a little bit of dichloromethane. Okay, so that is your product dissolved in dichloromethane. Let's take a closer look. Okay, now you don't have any water drop. The liquid is not cloudy and there is no floating water droplets. All right. So that is the purpose of adding a drying agent to a non-polar solvent like dichloromethane. This is the IR sample. I'm going to run the IR maybe off the record. I don't want to record that. There's nothing much to see on the screen. Okay, after running the IR, it is the remaining sample. Right? I didn't use much. I just used a drop of this liquid for taking the IR. The remaining liquid, I'm going to evaporate the dichloromethane solvent to get our product. Dichloromethane is a low boiling liquid. It boils at 39 degrees centigrade. 39 degrees centigrade is little above the room temperature, right? So once the solvent is boiled off, we'll get a white solid. That is the mixture of isoborneol and borneol. We'll do the NMR spectroscopy of that. I'm not going to do the melting point. We tried melting point in the previous semesters, but isoborneol would sublime before melting. Right? You know what is sublimation? The solid turns into gas, skipping the liquid phase. So there is no melting. It sublimates before it melts. The melting point didn't work in the previous semester, so we're going to skip that technique. Okay, so once all of the dichloromethane is evaporated, I'm going to remove the flask and cool it down to room temperature. Okay, zero down the whey paper and transfer your product on the whey paper. It is a waxy substance, so you need to really scrape it out. Okay, the weight of the product is 0.36 grams. The next step is taking NMR spectrum for this sample, but I'm going to run that off the screen.